forward now. And so let's dive into this dude. Now, again, notice if I said on a test, find every length, every force on every one of those bars, there's a lot of them there. And so that would be, 2 hours or something. It would take a long time to answer that, but you definitely could answer that. All I really want to do another question for is, because we need to get maybe a little bit better at just the process that we worked on Thursday, where you kind of pick like, what should I figure out next? Should I do this joint? Should I do that joint? And then secondly, notice, in a sense, thank God, they're only asking me for C, D, and CF, and CG. Let's see, I'm looking at that right now thinking, that's kind of a weird. I'm sort of surprised they didn't ask me for GF. Does that make sense? From what we did the other day, like I'd be able to chop that a little bit easier. So I'm sort of thinking out loud right now, like so based on the method of sections, what we learned the other day is that we can sort of fill in any of those triangles we want and treat it like it's solid, basically just saying, I'm not going to worry about the individual job each one of those is doing to keep this thing solid. I'm just going to, get on with it and worry about what I need to worry about. And so I don't know, where should I chop that, if you will? And actually it kind of strikes me because this question's, I don't know, feels sort of dumb. I think I am going to change this to GF.
So you say that because you think CG is going to be 0?
No, as one of my first thoughts, but notice there's a lot of other bars connected to it.
Oh.
Now, is there a 0 force truss in this? Well, there would be if this force wasn't here. Do you agree with that? Because this force right here could not push up or down if there was no force up there. Now, there is a force up there, and this is the only one that can fix it. So does it make sense I could like jump right there right now and that'd have to be 4? If it's pushing down 4, this is going to have to push up 4. It's the only one that can do that. There, I just found BH. So that's kind of the idea about skipping around. But again, what we're studying is we're saying, well, if you only want those 3 for some reason, then the important thing here is I'm going to fill in, let's go for the same color as the truss. I'm going to fill in all of these solid. Well, or fill this one in solid. And chop this truss right through these members I'm interested in. Now, would you agree I could actually work on the right side or the left side here? And it actually won't make any difference. Now, one of them could be easier than the other. My gut reaction is, well, the right side looks simpler. Maybe I should go over there. But I will give you extra credit. I'm going to pick one of the sides to do it, and you go do the other side. She gets the exact same answer. Doesn't make any difference. I'll pick the easy one. I'll do the right side, then you guys go do the hard side. However, honestly, although it looks harder, I don't think it is. I actually think it's just the same. I don't think it's going to actually be any easier or harder, to be honest with you. So I'm going to use the method of sections, which is, again, sort of code for fill in what you don't care about. And you are going to have a question on your test about this. Fill in what you don't care about. Thus ignoring those members. Okay, so I'm going to choose to draw that right-hand section over there. So, and this is true in a test too. Like if I ask for a free body diagram, you can be a little bit lazy. Like you don't, I usually don't put all the dimensions in because they're right there. Like I can see them. And so I'm filling that whole thing in, treating it like it's a solid. Now the question is, can you not screw up all the arrows that are on that thing? That's kind of what I'm curious about for you. From Thursday's work, can you fill all the correct arrows in there? Free body diagram. Well, shouldn't miss these. You got 5 coming down right here. Again, I'm going to be lazy. It says kilonewtons all the way across the top. And so it's like, that's 5 kilonewtons, but I don't want to have too much crowded in there. And then I got 3 going here. Where else do I have arrows, or am I done? Yeah, all of these that I chopped over here, like those are all touching my filled in triangle. So by filling it in, and I'm saying basically, I don't care about DE. I don't care about DE. I don't care about EF. I don't care about ED. I'm just treating that whole thing like it's solid and not worrying about them, only because, hey, you said I didn't have to find them. So fine, I won't. But I'm looking at these other ones saying, well, I got this one goes off this way. And again, as I said the other day, do I know it's tension? Do I know it's actually pulling left right there? Or is it actually pushing right? I actually don't know. And then I got this one that kind of takes off in this direction. And then I got this one that's not straight. So I'm purposely making sure this doesn't look straight. So I'm assuming tension for all of those. Now, can you appreciate there's a lot going on and those are all going different directions. I'm gonna have a really hard time reasoning out which one of those are tensions and which ones are compressions. Maybe I could do it. But as I said before, if we just assume tension, because it's either impossible to reason it out, or perhaps we're just too dumb to figure it out on our own. We don't have enough experience yet, myself included, to kind of guess and get that exactly right. Perhaps that's the case. Now, who knows the answer? I'm actually not done. My free body diagram isn't done. And if I don't recognize that, I'm SOL. What am I missing? Yeah, remember how we calculated before? There's a reaction over there. I mean, what do we have? 6, 10, 18. We have 18 kilonewtons going down. Well, remember, that means the bridge flies through the ground unless there's a reaction right over here and a reaction right over there. So those 2 reactions are going to have to total the same 18 that's going down, correct? And so in a sense, I should have figured that out before. Remember on the problems I gave you the other day, I said, that's actually, if you want steps, that's the first step right there. Fill the whole truss in solid and get those reactions. Now, in my case, I need the reaction at E. Therefore, does it make sense I could find it by doing the sum of the moments about A? Does that make sense? That's going to give me E, which is the one that I need to know. So I won't redraw the truss filled all the way in solid, but that's actually what I'm doing. We've already been doing sections. We said, hey, ignore what's going on inside the truss. Just make sure the thing sits there. And then we'll worry about all the individual bars that make it sit there later. So let's see, what are the sum of the moments around A? Well, I got 4 pushing down a distance of 5 away, and that's going to rotate clockwise, and so that'd be negative. So I got 4 times 5, and then I got minus the next 4, but it's times 10, and minus the next 5, and it's times 15. And then that 3 out there, and it's times 20. And so this thing badly wants to rotate counterclockwise around A. But fortunately, we have the force at E, and I'll even label it sort of completely correctly. Force of E at Y that actually wants it to go up. So I can say plus force of E at Y times also distance of 20. And that whole assembly's got to be equal to 0. And so, bunch of few buttons. Let's see, that's 20 plus 40 plus, somebody do this with me so I don't screw it up and we don't know it. 60 equals divided by 20. I got 9.75.
divided by 20 as well.
Yeah, so what I did was just,
Yeah, that,
I added all these to the other side, and then I divided by 20.
yeah, so I got
Sweet. So that, of course, is a really important number. But now I want you to think about this free body diagram over here and like what I can do to make my life a little easier. Because if I come back over here and I say, okay, well, there is a force right here of 9.75. Do I actually need the 3 and the 9.75? The answer is no. Can I put them together? I mean, if one's pushing down 3 and one's pushing up 9.75, couldn't I just cancel them and be 6? So you're more than welcome to leave this alone, but it would actually be better, be easier. Like I have just less stuff to screw around with, right? If I make that 6.75, so that's the net force, if you will, at that joint. So because I'm probably going to need these labels for stuff later on, I'm going to label all these points. This is D and this is F. And so now I'm ready to go. I've got 2 actual forces pushing on this thing that I do know, and I've got 3 that I don't know, and I need this thing to do 3 things. I need it not to rotate. I can't have this thing spinning, and I need it not to move up, and I need it not to move right and left. Notice it's 2-dimensional, so I don't have to worry about Z, as most problems are. So what I want to do is give you a second to think about this now, because this isn't new, and this is definitely something on a test, and this is definitely cool. Like this is something you definitely want to not leave this class not being able to do. You can make some mistakes, but can you at least figure out what am I going to start with? The idea is some of the forces in X, some of the forces in Y, or some of the moments around one particular point. And those are the only 3 choices, right? So I gotta pick something that I want to know. Some of the moments around F would be great for the Connor reason. Yeah, because you got two of your forces are eliminated by picking F, so that's an excellent idea. Of course, you should say that some of the forces in X would be a terrible decision, right? Because you got 3 unknowns in that bad boy. That'd be dumb. All right, I'm down with that. So phase 2, now that we know the reactions. Notice I never even bothered to find the reaction over there at A. Don't need to know it. I'm only worried about my little free body diagram. So some of the moments around F is an excellent idea. And of course, I need that to be 0. No matter what point I look at, this thing better not be rotating around it or bridge falls. That's free body diagram is tiny. So let's see, I got 6.75 trying to rotate it positive. And it is a distance of 5 away from F, is it not? And then I got 5, except for it's pointing right at F2. So I don't even need that one. That's kind of interesting, isn't it? So 5 actually makes no difference, and neither do either of these 2 down here. So the only one left is that force right there. Now, again, I can name these anything I want. I could call this force DC because it's aiming that way. But again, I'm just feeling like I want something nice and clean. So I'm going to call them force 1, force 2, force 3. So, wow, this is going to be a great choice then. So around F, of course, it wants it to rotate that way, which is also positive. What does that tell me right now? And yeah, notice over here, it's a distance of 3, which is not in my free body diagram. I could have put that over there, but I just thought it'd get too crowded. So, and that's it. That's the only things that are contributing to its rotation. But what do I automatically know is wrong right now before I even start? Does it make sense? F1 is going to come out negative here. Like the only way those are going to be 0 is if F1 comes out negative. So that just means, oh, I drew that arrow the wrong way. And so for that reason, I'm actually going to go fix this right now. I'm going to fix it right now. So that may need, I need to go unwind some things here. So I'm going to go back here. So as I mentioned before, the thing I don't like about this is I wish there was a way to like have my old drawing and sort of like make a new one or something, like maybe make two of them or something like that, because it's kind of neat to think that way. So of course, what does that change down here? This is negative. The F is negative because now it's causing negative rotation. Do you agree with that? And now F1 will actually come out positive and life will be good. So let's see, that'd be 6.75 times 5 divided by 3, which is 11.25. And I didn't have to round that. So F1 was 11.25 kilonewtons. And because of the arrow, let's see, let's rewrite this. Rewrite what we wrote the other day. We said if you're pushing out, if your response is to push out, that means you're being compressed. And notice I can recreate that for myself. I don't have to memorize this. I can recreate it. Whereas if you actually are pulling in, then we said that's tension. So that's why all my arrows were aiming out away from the point. That's why I was assuming tension. So that means this dude is actually under compression and my drawing is actually accurate. Like my drawing is fixed. And remember, as we said, there was no way all those arrows aimed left because that means it would be moving left in the X direction, right? So some of them had to be going right. Well, now we got some going left, some going right. Maybe it's correct now. Maybe those other two really are in tension. I don't know. This is a very complicated truss, so it's going to be maybe hard to tell what's in tension and what's in compression ahead of time by inspection. So I'm just letting it take care of itself. All right, that was awesome. Now what should I do? Can I do the sum of the forces in X if I want to? Now that I know F1. What do you think, Thomas? Can I do the forces in X now if I want to?
Yeah.
The answer is you can, but you're not going to be able to solve it. Do you see that? Because would you agree that force 2 has an effect on X, and because this is going left, it also has an effect on X, and that's two unknowns. So I don't want to do the forces, some of the forces in X. What about some of the forces in Y? Same thing. This one's going up, this one's going down. I'm going to have two unknowns. I don't want to do the sum of the forces in X, some of the forces in Y. Therefore, I'm sure hoping there's some other moment calculation I can make. Anybody have any storms of brain to share with us? What?
With momentum of D.
D.
All the X forces will be eliminated on F2 and F3.
Well, if you go D, then aren't both of these forces going to provide a moment? They're both going to try to get it to rotate, so I'm going to have two unknowns. I need one of these forces not to be involved in whatever my next calculation is.
I guess you could go over to moment around C.
That's exactly right. There might be another answer to this, but remember this point C up here. Both of these are pointing at C, aren't they? So it doesn't even have to be one of the points in the picture. So anything that F2 is pointing at or F3 is pointing at would work here. Do you understand that? So I could have also done G because that would have eliminated force 3. Now I can't do F because then they both get eliminated. Does that make sense? I got to pick something that only one of them is pointing at. Now that I know F1, I don't really care about F1 because I actually have a number for that one now. But I got to pick something that one of them is pointing at. So I don't know, I'll pick C. That was the first idea that Connor had. It's fine. So what are the sum of the forces, not forces, moments? What are the sum of the moments? Again, what are we trying to do here? We're trying to make sure no matter what point we look at, it isn't rotating. Now, this isn't not super simple. Do you agree that force 1 that we just calculated is not trying to get it to rotate around C? Because it's not pointing at it, but its tail is coming from it. So force 1 isn't making any difference, but 5 is. 5 is trying to get it to rotate around C clockwise at a distance of 5. And 6.75 is also trying to rotate around C, but it's trying to get it to go counterclockwise, so that'd make it positive. That's a distance of 10, is it not? And then the only one left, force 3.
You gotta do the,
X and Y.
yeah.
Good job. But unfortunately, this thing is not horizontal or vertical. It's pointing at some weird angle. So I either have to find the perpendicular distance from this vector right here over to here, which would be like somewhere right there, which we've said in the past, that's really hard. I could just say force 1 times this distance, but I'd have to do a lot of geometry to figure that out. We said earlier, it's actually usually easier to break force 3 into its X and Y components and do both of them separately. Now, that's going to cause there to be 2 F3s in this, but they're still just F3, right? Yeah, we'll just combine them and do a little bit of math. So let's see. And so for that reason, I don't want to call this force 3 of X and force 3 of Y, because then I am making 2 variables of it. I really would like to just make it 1 variable. So let's see, let's do the, let's see, it's aiming straight left. So I'm just drawing this in temporarily just so I can think. So that's like the X component of force 3. And that would be trying to rotate that way, right? Which would be negative. So it's force 3. But again, I got to modify it. Its horizontal component isn't force 3. What's its modification? Well, again, I got to come up with a rise over run over here of that shape. Notice it runs 5 and it rises 2. So this is over 2 up 5. So it's going 5 this way and 2 that way. That's the square root of 29 for the hypotenuse. And so now I have a sense of what proportions of it are in X and in Y. And of course, it would be actually better to, squeeze that onto the free body diagram over here. Just don't know if I can write small enough to get that done. That's terrible.
We're talking about F3.
F3.
Well, why F3 if we're doing?
Because F3 points straight to C, so I'm moving it or rotating. F3 is no, well, we said yeah, but F3 is pointing it down. So, clockwise.
So do you agree then that its modifier is 5 over the square root of 29? Now it's horizontal. So I'll even make a little note here. This is my horizontal modifier. Anything wrong? And now we have a distance to worry about. How far away? How far away is that, black line right there? Yeah, that's 3. So it's a distance of 3.
Oh, I'm looking at D.
That would be your vertical component as well.
Yeah. So then I've got kind of this vertical version over here. That's where it would be. So again, I have force 3, but what is that doing around C? Is that positive or negative? Well, notice C is over there. So it's also actually rotating it negatively. And so now I need, because force 3 is neither horizontal or vertical, I need its sort of vertical modifier, which would be 2 over the square root of 29. And how far away is that from C? It's 5. I guess there's no reason I have to erase this. I'll call this force 3 of X and force 3 of Y. They're not really getting in the way. I'm kind of okay with that. Because I have color and I can kind of say I can ignore the black ones. That kind of makes sense. So yeah, it's a distance of 5 away. And then that's finally it. That's all equal to 0. I have every force trying to get it to rotate So let's see if I'm going to add those force threes to the other side. So on this side, I have 67.5 minus 25. I'm going to show a few of the steps here. So I have this left on this side because I added those two numbers together. Then I'm going to add all those force threes to the other side so that they're not negative. And so we really have then force 3, and is it okay if I kind of multiply those together? 3 times 5 over the square root of 29, that'd be 15 over the square root of 29. And then this would be 10 over the square root of 29. You cool with that?
Wait, so.
I sort of factored force 3 out. Since they both had a force 3, I factored it out. And then I said, well, hey, this is 3 times this, and don't you multiply fractions straight across? So 3 times 5 would be 15. This is 3 over 1. 1 times the square root of 29 would be the square root of 29. Yeah, now notice for the first time, I just realized, hey, this is going to come out positive. Force 3 is going to come out positive, which is great because that means I sort of got lucky and that arrow is actually going the right direction. Now, just philosophically, I'll write this on the board. If you have a bridge that looks like this, even if it was circular, and you got a bunch of weight up here pushing down, and thanks to all of the members that are in this kind of going every which direction, basically, isn't this entire bottom here going to try to get longer? Is it going to be shoved on? So it's like, it's going to try to get longer. Well, if it's trying to get longer, then isn't it going to go? No, then arrows. So that's tension. So the fact that I drew that arrow out, that kind of actually makes logical sense. I guess in hindsight, I'm sort of not surprised that's right. It would be right. I really have no idea about force 2 because it's inside. And then it's kind of cool to note that, you know, you could even simplify this to 5 over the square root of 29. So really what I'm going to do then is take 42.5 times the square root of 29 divided by 5 times the square root of 29 divided by 5. You got 45.77 approximately. So force 3, 45.77 kilonewtons. Arrow out was tension, and we got a positive number, so that means that's right. So there's my second answer, very satisfying. Pulling type A here, can't live with that 9.
I was gonna say, yeah.
Yes, but I'm subtracting them, aren't I? Oh, no, I'm not. I'm adding them, aren't I? So I did some algebra wrong there. So let's stop here for a second. So I did some algebra wrong. I'll fix it. But like, how am I going to catch that? Like, is there a way I could catch that? Yeah, that's the first thing. I didn't think about it when I wrote it down. But 45 is drastically bigger than 9. And so that's kind of like, really? I mean, it could be. It's not that I know that for sure. And would you agree I made kind of an understandable algebra mistake? I mean, it doesn't excuse me because everybody died. But but yeah, good job. I heard you guys saying 25 and you guys were getting this right and I'm not. This is why I have to have an iPad because it's actually doesn't look bad. So the right answer should be times the square root of 29 divided by 25, which is only 9.15. Now I'm getting what you guys already got because you didn't make my dumb mistake, did you? So that does feel better because it's kind of like closer to the other one. But again, it's like it's hard to know. As we said the other day, like maybe there'll be something I can do to check this later on. I don't know. We'll talk about that when we get there. All right, so I actually know force 1 and force 3. Now I just need force 2. What are my options? Well, if you like moments, you can just find something that force 2 is not pointing at to rotate around. Does it make sense? You can pick any point on this paper, any of them, anywhere. Pick D, moment around D. Force 2 is not pointing at it, that'll work. Moment around E, whatever you want. But do you remember that some of the forces in X and some of the forces in Y are a little easier? Because moments, you have to take a force times the distance. So maybe that's a little easier. Or maybe like in my case, I'm just thinking, oh, let's just do it different. Let's just not do moment again. Should I do X or should I do Y? Does it make any difference? Isn't that kind of weird? It actually won't matter, but this is an example of how I could check my work. Like if I choose Y, then I'm gonna get an answer for force 2, and then I could go, well, gee, I wonder if all the sum of the forces in X are 0. So that's kind of cool. So it didn't occur to me until we just got to this point, but let's go do that. I actually don't have a good reason for this, but let's just pick the sum of the forces in Y. By the way, that's not that great of a choice. Why is it not that great of a choice? Because I have a ton of forces in Y. If I chose X, then a bunch of those will be eliminated, right? Where I was trying to be lazy and eliminate things. Since I wrote it down, we'll just continue, but okay, so let's see, I got 5 going down. I don't have to multiply by anything this time. I got 6.75 going up. Force 1 has no contribution to Y. Yes, it does. It is facing Y. So force 1 was going to the right. And remember, this is why it was so important we changed that arrow, because we would call it negative if we left the arrow alone, right? But we fixed it and it's going right. And so therefore it's positive here. And that would have totally screwed up this answer. What about force 3? Do I have to get it involved? Yep, it's going left and right. We correctly aimed the arrow left, and so it's going to be negative. And we said force 3 was approximately 9.15. What's wrong with that though?
You're using the full force, not the one portion of it.
Yeah, it's force 3 is not aiming left. I'm using the full force of it, and it's not full force left. I have to, well, modify it again. Same thing with force 1. That's exactly right. Or force 2, not force 1, force 2.
Yeah.
So we're going to need to do that again. So what's the modifier for that? Well, we did that a while ago. The modifier for the horizontal version was 5 over the square root of 29. So it needs that modifier. Good. I didn't do that on purpose, but it should be 2, right? Because isn't 2 the vertical one? So that was another accident. And then finally, force 1. So right now we have just a bunch of numbers. And so now we got force 1. I'm sorry, force 2 is the only one left, right? And again, I've assumed it's going left. And so I'm gonna write minus here, but I could be wrong, right? I don't know. We'll find out. The cool thing is I don't have to reason this out ahead of time. So I'm going to say minus force 2. But again, you stare at the figure up here. What's the ratio? What's the, you know, what direction is that force going from F to C there?
3 over the square root of 34.
Yeah, it's going up 3 and over 5. So it's rise and run aren't 2 over 5, it's 3 over 5. So again, it'd be kind of cool to squeeze this into this picture, but maybe dumb. Maybe I'll just leave out the other part, but 25 and 9, as you guys said, is 34. So that'd be the square root of 34. So what part of that is vertical then? 3. And then there's one other thing that is wrong here that is a mistake I made, but I did actually catch it. What is wrong with what I wrote here? What direction is force 2 going? It's going up. Positive. So I was kind of the other mistake I made, because I was kind of getting confused with what's X and what's Y. Like I got kind of spazzed out there a little bit. It's like, that's not hard to do, right? I like to do that. I like to make those kind of mistakes publicly. So, oh yeah, that's actually positive. And so again, if I get positive F2, that means I got lucky and it really is tension and I'm done. If it's negative, then I'm just going to go change that to a minus sign and change the direction of the arrow and name it correctly, and I'm done, right? So So I'm going to move all the junk to the other side. So that -5, I'm going to add it to the other side, 5, and I'm going to subtract 6.5 to the other side, and I'm going to subtract 11. Yeah. Remember what I was saying about being all confused about X's and Y's? Like there's no Y component to that, right? So thank you. Third mistake. Feeling good.
You're all amped up on sweet tea.
Yeah, I know the sweet tea is working me. Ha. Then I'm going to add 9.15 times 2 over the square root of 29. And so I moved that all to the other side and I got a positive number. So again, I'm a little worried that I screwed up just because I'm screwing up so much, but
Or it's small. Yes. Living can be smaller.
yeah, potentially. I did this before, so I'll look at my answer before. Oh yeah, I'm looking at it now. The answer is 3 something. So 96.8 times the square root of 34. And divided by 3. Did you get 96.8? I'm not
Yeah,
sure that's
3.24.
right. 5 minus 6.75 plus. Just so many things you can do wrong. Yeah, 3.2.
Yeah.
So, and again, I got lucky. It's positive, which means, and again, I want to emphasize lucky because it's not like I knew. I just got lucky. Force 2 then is approximately 3.2 kilonewtons. Arrow is aiming away from the point. We said that's called tension. Since it's positive, that proves we were right. So if I haven't made any mistakes, I'm done. But remember, if you guys aren't watching me, I just made mistakes on this. So what am I going to do now? I'm going to go back and sort of, well, as I mentioned a second ago, I'm just going to kind of hope for kind of a third thing here. I'm going to find something to check. But I would like to quickly just, I'm doing this if it's a test. I'm doing this if I'm actually going to build it. I'm going to have 3 people calculate all this stuff. And I'm going to check any possible thing I can possibly check before I, go build it. But do you understand you could do the moment around any point you want and check it? And we already did the sum of the forces in Y. So if one of our previous answers is wrong, the sum of the forces in Y will be 0 because we just made them be 0. But probably the easiest thing in this case would be the sum of the forces in X. But I have, as we did the other day, I've already calculated everything. There's no more forces left. And so this just better be equal to 0. And as I said, in my case, because I just screwed some things up, it wouldn't have been. And then at least I would have known to, go back and figure it out. It'd probably take me 2 hours to figure out what I did wrong. But now I can go do this. Some of the forces in X. And so what do I have? I have force 1 going right, which is 11.25. All my arrows are correct, and so I'm happy with that. I've got 5 and 6.75, but those are going up and down. I don't care about those. And then both of these forces are actually pulling left. Both force 2 and force 3 are pulling left as far as X is concerned. So they're both negative. And I'm going to go ahead and write this out a little bit more clearly. So minus force 2 minus force 3, because they're going left. But we have calculated those, right? So we actually know this is 3.2 and this is 9.15. And then, as we did before, we've got to modify those. So force 2, what was its modifier? This is why I drew this in this picture. So I come over here and go, oh, that's 5 over the square root of 34. That's force 2's modifier. And force 3's modifier is 5 over the square root of 29. So big question mark here. Does that equal 0? If it does, I'm done. If it doesn't, I'm not done. Again, I didn't use the convention I often do and say approximately, but force 2 and force 3 are approximately those answers. They're not exactly. So this is not going to equal 0, but it should be darn close. 11.25 minus 3.2 times 5 divided by the square root of 34. I see I forgot the 4 to write it down. And then minus 9.15 times 5 divided by the square root of 29. Check to see if I typed everything in right. I have to see if I typed what I thought I typed. Sweet, I got 0.01, which indeed is approximately equal to 0. So if you have time on a test, which you sort of do because I'm, giving your test at home, like I would actually prefer you check it, like even if that took a little extra time. Even if you kind of ran out of time and said, oops, something's wrong, but I don't have time to go figure out what it is. Especially, and if I as a teacher could go back and, look at all the stuff you wrote here and just see some kind of a simple oversight. Like you tried to include 11.25 in your Y calculations or something like that. So isn't that cool? I mean, stop and think about that. It's like somebody's designing this and we literally just figured out based on those 5 loads that are coming down on that truss, we literally figured out exactly how much force would be on each of those 3 members without having to find the others. But you can see from this, I could find them all. But it's kind of cool that you can actually section this thing up and just skip right over stuff and jump out to where you need to be. Again, extra credit, go do this same process, but do it from the left side. And you should get the exact same answers and the exact same orientations. In other words, what's tension should still be tension. I would say 2 things. Number 1, that's a great practice for this skill. And this is something that's going to be highly represented on the next test because it's one of the main things you want to walk out of this class knowing. So you need to be good at it. And then you know the right answer already. So that's cool. How are you feeling about this? We've sort of done 3 problems like this now. Maybe you need to practice some on your own, but I hope you feel a sense of power from this, I guess, and some sort of even if you're not an engineer, just the idea that you can walk into a house and see all these trusses and just have a sense of like, oh, snow's on here and that's going to cause this to push there and this to push there. And, all of a sudden it's like, yeah, can I get that whole thing to stand up? I mean, that's really cool.
How do you introduce like the Z factor?
Yeah, so it wouldn't be any different. We just have to do this more. We do the same thing we're doing, we just do it more. Fortunately, almost everything, everything that we deal with in engineering, you have gravity, which is going straight down. And so the only forces are going straight down. And so a lot of times there is no left and right even to some of these forces. Interestingly, notice if that thing was filled in, there would be no left and right at all. But because we're saying, well, let's save money and not fill it in, then some of these members are hooked on sideways. And so a vertical load causes a horizontal load. But again, they all have to work against each other because there isn't any external forces that are left and right. So the left and right forces in there have got to all kind of push and pull against each other to balance it out because this thing can't be moving. Ultimately, it won't be moving. There's no external forces trying to get this to move. Okay. So now we do the cool thing, which is let's do this for real. Let's do this for real. This is beyond your book. And this is the kind of thing that will, I think, deepen your grasp, but probably more importantly, like this is the thing that'll make you employable. Like what you just did is kind of neat, But now we're actually gonna notice there's no loads on this truss right now. We're gonna load it ourselves, like with real, and those are the real loads. I've told you this before, but snow load, at least down here in the valley, 25 pounds per square foot. Notice the units, square foot. Every square foot has 25 pounds of snow on it. That's not the same as Mount Ashland. We talked about that. So then you have dead load, which is roofing paper and so forth. And then you also have the ceiling. Notice the ceiling right here has weight too. You hang sheetrock on the inside of the house. And so it's not just the top, it's actually the bottom. And so what I want to show you now is kind of how to load. How does that turn into anything? And notice this particular truss is called a Howe K truss. And you can sort of see a K shape in the web in there. And notice, and I stole this right out of something called the truss, I won't say the truss Bible, but that's not the right word. It's I'll think of it in a minute. Notice this particular design with that amount of webbing in it is for 24 to 36 foot trusses, but you can appreciate if you say, oh no, I need to go 80 feet, you're gonna have more webbing in there, right? You're gonna have more junk in the middle because basically a 2x4 will only span so far. Now notice this is kind of cool down here on the bottom, but do you see how there's a little plate there? Like right in the middle of nowhere. Why is that? Well, that's because you can't buy a piece of lumber that's 36 feet long. The longest lumber you can get is like 24. So you're going to put a 24-foot piece here and then use one of those little connectors that I was describing the other day. And then the other 12 will be over here. And so every one of those, this is kind of a cool drawing because every one of those plates is actually holding that whole assembly together. And so, okay, let's load this truss. Now, here's what I said the other day. I hope this is at least reasonably clear. But these trusses are, I don't think I did say this on here. These trusses are typically 2 feet apart. So since this distance from here to here is 2 feet, then would you agree, as I said the other day, that this truss right here is responsible for 1 foot on this side of it and 1 foot on this side of it. So it's got a 2-foot stripe of snow on that truss. And of course, when you get over here, then this truss takes the next snow. You see what I'm saying? So it's not complicated like that. Because it's 2 feet on center, that truss is going to carry 2-foot stripe of the roof. Now, we are doing a 36-foot truss. We're doing the biggest truss possible. What does that 36-foot mean? It means this distance. Squeeze this in. That distance is 36 feet all the way through. And that's how much snow is going to land on it is 36 feet. So this is a little bit weird. Does it make sense that top chord is longer than 36 feet? It's like the hypotenuse of a triangle. So do I think of the length of that truss as being, longer than that, or do I just treat it like 36? Well, because snow falls vertically, you just get to treat it like 36, which actually isn't obvious. So let's see. I have this picture on the back page then for you to kind of add some work to. So I drew the truss out for you just and labeled all the points and so forth so that we can start calculating it. And this is actually kind of a project. Like I'm not going to do this for you. You're going to do it and we're going to kind of do it together. But again, let's first load this thing and let's think about how much force is actually at every one of these joints. And so let's see, up on the roof then, does it make sense I have a total of 40 pounds per square foot? In a sense, I don't distinguish between what's live and what's dead. Worst case scenario, I have 40 pounds a square foot. So maybe it doesn't have snow on it on a particular day, but I need to make sure it can handle it if it does. And so I have a total of 40 pounds per square foot up there. Well, because that is a 36-foot long and 2-foot wide stripe, isn't that a total of 72 square feet times 40 pounds per square foot? Please interrupt if the logic of this isn't making sense to you. So I end up taking 40 times 72. which is actually 2,880 pounds. Notice the units cancel out. So that's how much weight is on the top of this, just one truss, not all the trusses. I just have to figure one truss and then all the trusses will be the same. You agree that has a combined load of 2,880 pounds all the way across it? Maybe I'll take the time to like draw that in there. That's actually the truss. The truss is,
We're basically finding the maximum. The snow is in, like you said on the other project where it's live load.
yeah. So we're treating it like the live load is there because that's worst case scenario. It's got to stand up if there's snow on it. And again, it's just like, you know, like right now I'm lifting this pen and I'm not working very hard. But if suddenly something heavy lands on my hand, well, now I'm working harder. So, you know, we got to plan this truss to be able to handle the worst load it can get. But most days it's just going to be sitting out there in the sun like right now, and it's not going to have to work that hard. It's capable of a lot more than you're asking of it. But do you agree the problem is like, where do I put that 2,880? Where does it go? Like earlier, didn't we have arrows like coming down on the truss in just a couple of places?
Would it be on each?
Wouldn't it be what?
On each? 'Cause it's
Not all of it. Like, isn't there snow down here, right? Think of this as like snow's piled up everywhere. Like, isn't, so it's not all on H.
You'd have to split into the sections of AJ and JH and H.
So would you agree this is symmetrical? Like, it's not like the previous problems where I just had some weird weight somewhere. Well, would you agree I kind of have like 4 regions of the truss right there? If I take 2,880 and divide by 4, I actually get 720. So kind of in this range. I'm going to erase this. Actually, I'll do it up here. And I don't have to erase it. So up here, I basically have like 720 right there. And then I have a total of 720 there, and the same things over here. You agree with that? Because isn't that where the snow is? The snow's everywhere, right? And by the way, this is what we're studying next is continuous loads like this. But now let's think about this. What does this mean? Well, this means that this, because this actually isn't a line, it's a board. It means that that board must be strong enough not to bow down too much to the point where we say it fails. Does that make sense? So it is very possible that there's enough snow that that board just goes snap, you know, and then that's not good. And that's part of the reason why this says don't go over 36 feet. Because would you agree if this is 36 feet long, then each one of these is 9 feet? And so this length isn't 9. It's a little longer than that. But a 2x4 will do that. And that's kind of why they say don't make this truss if it's over 36 feet. You got to add some stuff because a 2x4 won't span further than that. And so that's kind of what's going on. So does it make sense? We're just kind of assuming the board that you put there is going to be effective then. Now, here's the cool part. So if that's the case, does it make sense? Half of that 720 would be here because it's symmetrical, and half would be here. It's going to get transferred to that. And again, think about it like this. The standard, the classic construction technique is to have a posts and a beam. And so if you have 500 pounds up here on top of this, and now you have a hole in your wall for a window or a door, then that's going to take the 500 pounds, which actually wants to be everywhere. And it takes all of this load and pushes it out to the side. And of course, that's going to put half of it here and half of it here. You agree with that? As long as it's symmetrical, and we had problems that weren't, and they were weird, and we had to do moment calculations to see how much went in each spot. But if it's all equally distributed across there, then that's how much is going to go to each spot. You had a thought, Caesar?
Yeah, because you're gonna get the next section of the 720 with that 250 from that section add on to the.
Yep.
BJ
So this next
or 360.
720 is going to have 360 here and 360 here. And this 720 on this side is going to have 360 here and 360 here, and this last 720 is going to have 360 here and 360 here. So what's the net effect then of all of this snow? You need to add this to your sheet. You've got a point load of 360 here, a point load of 720 here, a point load of 720 there. Now, does that add up to 2880? Which is the weight that was on this thing? Yes. So do you see where those arrows come from? That we were just kind of thrown on the problem a second ago? Like, you got to figure that stuff out. There are no arrows pointing at anything in the real world. You have to put that load there yourself. And you don't do that anywhere in any of this class, like as far as part of the book is concerned. Now we got to do the same thing on the bottom though, don't we? Because we got arrows on the bottom too. It's just that the bottom is only dead load because nothing comes and goes from the ceiling. You just have sheetrock there. That's the only thing that causes that load. Maybe light fixtures. I mean, there's a few things there. They also plan it, by the way, because there's stuff in the attic like insulation and ductwork and things like that. So it's not just sheetrock, but it's just junk that's permanent, including the truss itself. And so would you agree then the ceiling is also 72 square feet, but it's only multiplied by 10 pounds a square foot, so a total of 720 pounds. So we have a total of 720 pounds on the ceiling. And so let's go add that in. Notice this particular design has this joint right below that joint and this joint right below that joint. So you do this one. I'm just going to give you a head start right lightly in case you screw up, because I want you to all have the right loads before you take off and try to figure the whole truss out.
So for the 360s we had, because like that little corner is kind of, I don't know where I
What do you mean by that corner?
yeah, the corner.
They don't, the ceiling.
You're talking about this point right here?
Right, like, point A, B.
So you have a total of 720 pounds on the entire thing, but it's spread equally all the way across there. So just like last time, we had to divide 2880 by 4 to see how much of the weight was in each of the 4 bays. Same thing, divide 720 by 4. So you get 180 in each bay. You agree with that? But then half of that 180 is over here and half is over here. The next one, half is over here, half is over here. Next one, half is over here, half is over here. So
They also have, since we have 720, would be the first one, I guess, which would be 180. Would that add with the 720? Create one single force going down in that one?
yeah, so we do want to put the 360 and the 90 together. So those were continuous loads, meaning everywhere, and we've now just reduced them to what are the loads on each of the joints. So notice there's loads everywhere, but what's really cool about the fact that this is symmetrical, if I say find every single member, the right side's the same as the left. So you actually don't have to find them all. You just have to find the left side and you're done. So let's fix one thing. If you have 360 going down over there at point A and 90 going down, isn't that a total of 450? Sort of reluctant to erase that, but
But it's only gonna add. Right, because there'd be a wall that.
yeah, now remember, even still, we're not done because all of those forces are down, which means the truss is falling through the air, right? We can't have that, but isn't there some reactions? Notice this is sitting on a wall. Isn't that the first move every time, is to figure out what those reactions are? Again, what's cool about this is ours are symmetrical. How much weight do we have? How much weight do we actually have total? Don't we have both? That's all of our weight up there, right? So if we just take that weight and cut it in half, isn't that the reactions? Because they're not different. Like they're split evenly like we did on the board. So if I take 2880 plus 720, I get 3600. I cut it in half and I get 1800. So I don't think I'm going to get rid of that actually. I'm going to come back here and say 1800. That'll be left behind. And so what do I have? I have 3,600 going up thanks to each of those two walls. And if I add all of those, well, all of these reds and blues I have over here, that must also be 3,600. Of course, I should check that. So just to be careful, if I add those three blues, the three reds, and those two blacks, I should get 3,600, a total of 1,800 in each one. And that would mean, okay, good, the truss is not falling through the air. Now, again, is it a given that your wall can support that? No, like, how would you build a wall out of styrofoam? Like, it's not going to support that much weight. Does it make sense then, actually, sum total, what do I really have? I really have 360 going down, 90 going down, and 1,800 going up, which means even this 450 isn't right. Do you understand that? So 1,800 minus 450 is actually 1,350. That's actually the sum total now.
Well, I got caught up for a second.
I'm glad you asked. I came back here and I said, we had 2,880 pounds on the roof. We had 720 pounds on the ceiling, all going down. So I added those together and got 3,600 pounds. And so it's like, and again, notice we're oversimplifying this because how much does the wood weigh? 0. We're treating the wood like it is in there. That's not really fair. This is actually, we're really oversimplifying this. Wood weighs stuff. So we actually, this would be worse.
So that's assuming.
But I got 3,600 for that. Therefore, the walls better be pushing up at 3,600. So do you agree? I'm done now. Like you're ready to go. Now you're turned loose. So what I want you to calculate is just these trusses. As I said, does it make sense to you that if you find those, what is that? 1, 2, 3, 4, 5, 6. If you find those 6, the right side's identical because everything is symmetrical here. So I don't have to do quite as bad of a problem. So you have the next 15 minutes or so. Again, get something else to drink. And I want to check this
Out of
against what you
curiosity,
get.
can we not combine that 720, 180? Or is it really important?
No, because they're actually at those locations. Those are very location sensitive. So yeah, together they're a total of 900, but where would you put it since the weight of the snow is at J and the weight of the sheetrock is at B, and so you can't combine those.
Okay.
And you're going to see that because only 720 is up at J, that's going to kind of, that part of the 900 is going to affect AJ and JH, but the 180 is not touching AJ and JH. And so it is important to keep those separate actually. So it's interesting that every single joint has a force on it, and we loaded this ourselves. That's kind of cool.
Is it the reason why we don't combine them, because only the 720, a portion of it is applied to the 180?
Well,
Everything else is good
it is combined in the sense that, you know, that's a total of 900 pounds in that plane. But can you appreciate that only 720 of it is actually pushing down on this member right here?
Yeah, so I say part of it is being split to the side and also down and to the right as well, 14.
Yeah. So the problem is if I combine it to 900, I wouldn't be able to put it in the correct location. If I put all 900 up here, then suddenly this member is doing more work, and it really isn't, because that 180 is actually down here in a different location. So the only reason I could combine these is every one of them was coming from the same point. Does that make sense? They were all touching the same point. And again, if you like pain, leave them all there. You don't have to add them to 1350. Again, it'd be smart for me to add up the 3 blues and the 3 reds here and make sure I get, what is that, 2,700? Since the blacks are pushing up at 2,700, I'm going to do that really quick. What is 720 times 3 plus 180 times 3? Yeah, 2,700. So I just double checked. Some of the forces in Y are 0. So fortunately, this truss is not moving. Now I've just got to figure out how much force is on each of those individual members. So again, this is the domino effect now. Which joint should you tackle first? Don't tackle joint J. That'd be really dumb. Right? 4 unknown forces connected to J. Don't go there first. Could you go to B first? Yes, you could go to B right now. Do you understand why? It's got 180 going down. There's only 1 bar connected that we can solve it. You could go to B right now. Can you go to C? No. Too many bars. There's 3 bars connected, or members connected vertically. So I don't know which ones are doing what with respect to keeping 180 from going down. Remember, every one of those joints wants to go down. And so all these connections we're making here are going to say, nope, you can't go down.
That's not serious, would it be B or D?
B or D?
Yeah.
Yeah, they'll be symmetrical, so I don't really have to worry about B and
yeah.
D. Just pick one. You can go to A and you can go to B. Either of those 2 places, but you better not go anywhere else because there's too much going on. Yeah, so you have 1350 going up, but don't you only have member AJ that can stop that? Member AB cannot stop 350 because it's connected horizontally. It's not able to affect. It doesn't have any strength, but AJ can push down. So for that reason, right now, you know that this arrow has to be going that direction because it's the only one that can push down. Because remember, we got the whole truss knot to move, but right now we're thinking of it as being filled in. But now we're switching gears and saying it's not filled in. We got to look at each joint one at a time and make sure each joint doesn't move. The truss isn't going to move, but we got to make sure each joint doesn't move. And if there's an arrow aiming out over there, there will also be an arrow aiming out over here. So I'm going to stop sharing this screen and answer this myself because I don't know the answer. Thought I might have it in my notes, but I apparently don't. And I am going to share it with you before you leave, but I'm not going to do this for you. I just want you to check your own work.